Let's dive into the differences between the two runs presented in your EEG seizure detection application. Key observations from the two runs. 1. Test accuracy. Run 9 achieved a test accuracy of 96.67%. Run 10 had a lower test accuracy of 90%. This indicates that Run 9 performed better overall in correctly classifying seizure and non-seizure events in the test dataset. 2. Average training and validation accuracy. Run 9 showed an average training accuracy of 82.89% and an average validation accuracy of 93.04%. Run 10 had a training accuracy of 73.06% and a validation accuracy of 85.78%. The higher average accuracies in Run 9 suggest that the model learned more effectively from the training data and generalized better to unseen data. 3. Loss values. Run 9 had an average training loss of 0.4323 and an average validation loss of 0.3520. Run 10 had higher loss values with an average training loss of 0.5729 and an average validation loss of 0.5109. Lower loss values in Run 9 indicate that the model was better at minimizing error during both training and validation, which correlates with the higher accuracy achieved. 4. Confusion matrix. In Run 9, the confusion matrix shows that the model correctly identified 30 non-seizure events and 28 seizure events, with only 2 false negatives, seizures incorrectly classified as non-seizures, and 0 false positives, non-seizures incorrectly classified as seizures. In Run 10, the confusion matrix shows 30 correct non-seizure classifications and 24 correct seizure classifications, but with 6 false negatives and 0 false positives. This suggests that while both runs did well at minimizing false positives, Run 9 was significantly better at minimizing false negatives, which is crucial in a clinical context where missing a seizure could have serious consequences. Number 5. Training time per epoch. Run 9 had a training time per epoch of 0.60 seconds, while Run 10 took 0.91 seconds. The longer training time in Run 10 could be due to increased complexity or changes in the dataset size, but this additional time did not translate to better performance. Summary of differences. Run 9 outperformed Run 10 across most metrics, achieving higher accuracy and lower loss. It was also faster to train, suggesting more efficient learning. Run 10 had a lower test accuracy and more false negatives, which indicates it struggled more with correctly identifying seizure events compared to Run 9. The differences between the two runs could result from variations in hyperparameters, like learning rate, number of epochs, or batch size, the specific dataset splits used, or random initialization of the model weights. Implications for improvement. The results suggest that the configuration and hyperparameters used in Run 9 were more effective, and we might consider using similar settings or exploring variations around them to further optimize performance. Minimizing false negatives remains critical, and Run 9 shows better potential in this area, so future models could be fine-tuned based on its configuration to further reduce these errors. If any viewers have questions or thoughts about what might be contributing to these differences or want to discuss possible changes to the model setup, feel free to share in the chat. Given that the dataset remained the same for both runs, the differences in performance metrics likely stem from variations in the model settings rather than the data itself. Let's look closely at the model settings for each run to understand why these differences occurred. Analysis of model settings. Upon examining the settings, we can see the following similarities and differences. 1. Batch size. Both Run 9 and Run 10 used a batch size of 64. This setting controls the number of samples that are processed before the model's weights are updated. Since both runs have the same batch size, this parameter is not a contributing factor to the performance differences. 2. Epochs. Both runs were trained for 100 epochs. This is the number of complete passes through the training dataset, and since it is identical in both runs, it doesn't account for the difference in performance. Number 3. Initial learning rate. Both runs used the same initial learning rate of 0.001. The learning rate determines the size of the steps the model takes towards minimizing the loss function. Given that this setting is also the same, the learning rate does not explain the differences in accuracy and loss. 4. Data augmentation. In both runs, data augmentation was set to false. This means that no additional transformations, such as rotations, flips, or shifts, were applied to the training data to artificially increase its size and variability. Since this setting is the same, it does not contribute to the differences observed. 5. Shuffling. Shuffling was set to true for both runs, which means the data was shuffled before each epoch to help the model generalize better by reducing the likelihood of overfitting to the order of the training data. This identical setting does not explain the performance differences. Conclusion. Given that all the key model settings were the same across both runs, the differences in performance likely arose due to the stochastic nature of neural network training. Factors like the random initialization of model weights, slight differences in the order of data during shuffling, or the inherent randomness in the optimization process could all contribute to these variations. It's common for models, especially deep learning models, to exhibit some level of variability across different runs, even when the settings and data are kept constant. Summary and reflections. As we've seen in this application, even when the data and model settings are kept the same, differences in performance can still occur between runs. This highlights an important aspect of working with neural networks. Sometimes, the process involves a bit of unpredictability. Small differences in the initial setup, like the random initialization of weights or the order in which data is processed, can lead to variations in results. But don't let that discourage you. This variability is a normal part of machine learning, and it can actually provide valuable insights. Each run teaches us something new about how our model behaves, what it excels at, and where there's room for improvement. We invite you to experiment further with different configurations or try out new data sets to see how these factors impact model performance. Have questions or thoughts on what might be causing these differences? Or perhaps you have suggestions on new settings or parameters to explore. Share them with us. We're excited to hear your ideas and engage in a discussion about how we can continue improving this tool together. Feel free to reach out or dive deeper into the dataset and the model by exploring the links and resources provided. Model training performance. Comparing the last two runs. In our recent experiments with the EEG seizure detection model, we conducted two separate training runs using identical datasets and model configurations. Despite keeping the dataset and model parameters consistent, we observed some interesting differences in performance metrics between the two runs, which highlights the nuances and complexities inherent in training deep learning models. For both runs, we used a batch size of 64, which defines how many samples the model processes before updating its internal parameters. The number of epochs, or full training cycles through the entire dataset, was also kept constant at 100. Additionally, we set the initial learning rate to 0.001, a parameter that controls how much the model's weights are adjusted with respect to the loss gradient. No data augmentation was applied, meaning the model was trained solely on the original images without any artificial alterations or transformations, such as flips or rotations. Finally, we enabled shuffling for both runs, ensuring that the order of training samples was randomized each epoch to help the model generalize better. Despite these identical settings, we observed variations in the performance metrics. In Run 9, the model achieved a test accuracy of 96.67%, with an average training accuracy of 82.889% and an average validation accuracy of 90.04%. The corresponding training and validation losses were 0.4323 and 0.3520 respectively, indicating a relatively good fit with a low margin of error. Conversely, Run 10 showed a test accuracy of 90.00% with an average training accuracy of 73.06% and an average validation accuracy of 85.78%. The training and validation losses for this run were higher at 0.5729 and 0.519 respectively. This suggests that while the model still performed reasonably well, it did not generalize as effectively as in Run 9. These differences, while appearing significant, are actually a common occurrence in the field of machine learning. Neural networks, especially deep learning models, are influenced by various stochastic factors, such as the random initialization of weights or the random order of data presented during training. Even with identical settings, these random elements can cause slight variations in model performance. The lower test accuracy and higher losses in run 10, for example, could be the result of less favorable initial conditions or subtle differences in how the model encountered the data during each epoch. Understanding these variations is crucial as it underscores the importance of running multiple experiments and not relying solely on a single run to judge a model's effectiveness. It also highlights the necessity of careful parameter tuning and the value of techniques like cross-validation to ensure that the model is genuinely learning patterns that are generalizable beyond the specific dataset it was trained on. Overall, these results remind us of the inherently probabilistic nature of machine learning. The key takeaway is to embrace the variability as part of the learning process, continually experimenting with different configurations and techniques to achieve the most robust and reliable outcomes. We encourage you to explore these concepts further by experimenting with different settings or data sets, and to share your findings or questions as you engage with this evolving tool. Your insights and feedback are invaluable to us, and together, we can push the boundaries of what's possible in the realm of EEG seizure detection and beyond. Explore the EEG Seizure Detection tool, slybonichouse.com/rhythmscan.